When the random variable we are collecting is categorical rather than quantitative, we cannot have a distribution. In fact, we can't even build a histogram. All we can really do is to count the outcomes of the categorical variable and build a frequency table. Let's consider a sample of observations drawn from a larger population, just as we did for the fish in the lake. But this time, rather than focusing on a quantitative variable such as the fish weight, let's consider a categorical variable instead. Let's further simplify the categorical variable so that it only has two outcomes, which for statistical purposes we shall call success and failure. For example, imagine the flipping of a coin, which we have already defined as a trial, where we could define the outcomes heads as a success and tails as a failure. If we flip the coin once, we expect 50% of outcomes being successes, heads, and 50% of outcomes being failures, tails. But if I flip the coin, let's say, 10 times, would you be surprised if the tally consisted of 3 successes and 7 failures? No, because we are well aware of the concept of sampling error and the random variation of outcomes. If you use the variable x to count the number of successes in our 10 trials, we can define the empirical probability as x over n equal to 0.3. Because this empirical probability is in fact a proportion of successes out of a sample size 10, we shall henceforth talk about x over n as a sample proportion and use the symbol p hat for it. Note that many texts use the symbol p bar instead, but it represents the same concept. So please don't get confused by it. P hat or p bar, potato, potato. But what if I flip the coin 100 times? Would you be surprised if the sample proportion of successes was still 0.3? Yes, because this time, in order to obtain the same sample proportion as when we only had 10 trials, we would have to observe 30 successes and 70 failures out of 100 trials, which is, intuitively speaking, far more unlikely. That is because, as the sample size increases, the variation of the possible empirical probabilities around the theoretical probability decreases. We have considered this very concept when we introduced the law of large number last lesson. We can demonstrate this graphically with a simulation that collects all the possible combinations of tossing a coin 10 times. In other words, the whole sample space, which consists of 2 to the 10th, or 1024 outcomes. But many of these outcomes are more common than others, as they involve a more symmetrical number of successes versus failures. So it should not come as a surprise if the distribution of sample proportions look like this. If we toss a coin 10 times because we expect each coin toss to be independent from the others, then the theoretical probability of a success, where a success is defined as heads, for example, is 0.5. We indicate this theoretical probability of success with the letter p, and from now on, we shall call it the population proportion of a success, because if you kept tossing the coin until our arm fell off, the law of large numbers would dictate that a theoretical probability and empirical probability are one and the same. We also define with the letter q the complement of p, which is the population proportion of a failure. In blue, we have depicted the histogram for the sample proportions of successes out of all the 1024 different outcomes that are present in a sample space of 10 coin tosses. Can you recognize the familiar symmetric and bell-shaped distribution? To the left, we have written the expected count of successes and failures out of 10 trials, which is, of course, 5 each. It can be mathematically demonstrated that if we have enough trials, view them as independent events, so that we expect at least 5 successes and 5 failures, the distribution of outcomes can be approximated by a normal model with mean mu equal to the population proportion p and standard deviation SD of p hat equal to the square root of p times q divided by n. We call this normal model the sampling distribution for proportions. But what would happen if the population proportion, read the theoretical probability, for success is not 0.5? Then its complement q would not be 0.5 either. Let's rerun the same simulation of 10 trials, but this time let's assume the probability of a success to be 0.2. In this case, we expect only 2 successes and 8 failures. As you can see from the result of the simulation, the histogram of the sample space outcomes is no longer normal. Remember, however, that we stated that we need to expect at least 5 successes and 5 failures to approximate the outcomes with a normal sampling distribution for proportion. Here, we do not have enough successes to approximate the sampling distribution for the proportions with a normal model. Therefore, let's increase the number of trials to 25. Now, we expect 5 successes and 20 failures. And the histogram is normal again. So let's summarize our findings. If you have a categorical variable with only 2 outcomes, a success and a failure, and if you collect a representative sample made by independent observations that is large enough so that we expect at least 5 successes and 5 failures, then we can approximate the sampling distribution of proportions with a normal model having mean mu equal to the population proportion p and standard deviation given by the square root of p times q divided by the sample size n. Let's now see if we can apply the theoretical concepts seen so far to a more practical problem. Also, because we have talked enough about fish, let's change the subject and talk about apples instead. After all, we all want a balanced diet in life, right? Let's imagine that you own a beautiful apple orchard. And let's also imagine that you and your brother, yes, you also have a brother, collected all the apples, packed them into a total of 80 crates, and loaded them into a truck. Then, you head out to a fresh produce accepting station that belongs to a large grocery store chain, in the hope to sell the whole truckload of apples at a competitive price. You also happen to know that the quality control inspector at this particular accepting station applies the following methodology to inspect the quality content of the truckloads of apples. First, the inspector unloads all the crates. Then, he randomly selects 1 apple from each of these crates and pools all the apples in a single sample. By the way, we call this sampling methodology multi-stage sampling. Then, the inspector tallies the proportion of bad apples, such as apples with discolorations, blemishes, worms, and so forth, and if such proportion exceeds 6%, he will reject the whole truckload, bar none. Now, it so happens that you know, because you loaded a truck with your brother yourself, that as many as 8% of the apples in the truckload are actually bad. The question is, what is the probability that the inspector will accept the truckload anyway? To solve this problem, we need to use the sampling distribution for proportions. But before we can assume that the sampling distribution for proportion follows the normal model, we need to verify the set of assumptions. First, we know that a sample was collected randomly. Therefore, we can safely assume that the apples in a sample are independent from each other. Second, because a sample was collected randomly, we can also safely assume that such sample is representative of the population of apples in the truck. Third, we expect at least 5 successes and 5 failures because 8% of 80 apples is 6.4 apples, which is greater than the minimum number required of 5 successes. The expected number of failures, of course, is actually much higher, so we don't have a problem there. We can now represent the sampling distribution for proportion of sample size 80 extracted from the population of apples in the truck as a normal model will mean 8% and standard deviation equal to 0.0303 or 3.03%. We can now calculate the area of the tail of the normal model to the left of 6%, the acceptance criterion posed by the inspector, which corresponds to the probability that a truckload will be accepted. After we calculate the z-score, we can now use Excel to estimate a probability of about 25% that a truckload will still be accepted.